Hello, this is Dan Explains, and I'm Dan. Life is pretty resourceful. If there's an environment on Earth, there seems to be life adapted to it, even when there's no air or food. There are things like anaerobes that don't even breathe, or the colorful bacteria growing in the hot pools of Yellowstone, which breathe all sorts of other compounds like sulfur, which is like oxygen's big brother, chemically speaking. Of course, there are plants which essentially consume light for energy instead of food, but nothing on Earth can survive without at least a little bit of water. Even the hardiest life needs at least a little. But are there other substances that could work? Maybe one even better than water? Maybe there is. Let me explain why. One of NASA's mantras when it comes to looking for life in space, and yes, I mean alien life, but not little green men per se, is follow the water. Of course, the only example of life we have, Earth life, needs water to survive. This hasn't stopped NASA from flirting with the idea that there may be life out there that uses a different solvent besides water. One of the leading candidates is ammonia. Yes, that stinky stuff used in cleaning solvents. It may not seem like a good solvent for life from our perspective as water-loving life forms. However, it's got some things going for it, and one thing that may make it even better than water as a solvent for life. Now, by better, I don't mean it's more likely. There is more water in the universe than ammonia. I just mean, given the right conditions, ammonia life may develop more easily and possibly even advance in complexity faster than water life. Okay, so what does ammonia have going for it? First off is its properties. It's very close to water. Water molecules have 2 atoms of hydrogen and 1 of oxygen, forming this sort of bent structure. This causes an imbalance in the electrons around the molecule, making it what's called polar. Kind of like a magnet with a north and south pole, but not using magnetism. This makes it a very good solvent with a high surface tension. Ammonia molecules are made up of 1 nitrogen and 3 hydrogen. The nitrogen atom attracts 1 more hydrogen because it's left of oxygen on the periodic table. Fluorine over there on the other side would bind 1 less hydrogen than oxygen does, for example, but that's a discussion for another video. Anyway, ammonia binds 3 hydrogen and is bent in a similar way to water. This creates a polar molecule, making ammonia good at acting like a solvent in a similar way to water. Another thing that ammonia has going for it is that it's highly abundant. Not as abundant as water, sure, but there have been clouds of ammonia found in space. So, abundant enough that if planets formed around stars in these clouds, they could have oceans of liquid ammonia rather than water. Since nitrogen can bind 3 atoms, it makes it good for acting as a building block for potential ammonia-based proteins. In fact, nitrogen is even used as an important part of our own proteins, since it combines with 2 carbon atoms to form the peptide bond, which is critical for protein structure. So, how is it better than water? Well, ammonia does one thing that water can't. It dissolves metals like water dissolves salts, which, by the way, it can also dissolve. Not all metals, of course, but reactive alkali and alkali earth metals over on the left side of the periodic table. These are some of the most important metals for life processes, like calcium and magnesium, for instance. Putting pure samples of these types of metals in water often ends in a spectacular result. It's not just the fact that these metals dissolve that's such an advantage. It's why they dissolve. They dissolve because the electrons separate from the metals floating freely in the ammonia, creating what's known as a solvated electron. Our water-based life has to play a lot of chemical tricks to move electrons around. It's one of the reasons why we need to breathe, for instance. Our cells need a place to dump our low energy electrons, and they need a reactive oxygen to do it. Okay, yes, that's a bit of an oversimplification, but this is a short video, not a college course in biology. Also, plants are green because photosynthesis works by passing an electron up to higher energy levels using light like a bucket brigade. With ammonia, those complex chemical mechanisms might be able to be simplified with electrons just floating around in solution. Instead of needing to use chemical processes to increase and decrease electron energy, it could be done through increasing or decreasing electron concentration or temperature. Cold ammonia life is even depicted in some stories and games, like the Thargoids from Elite Dangerous. But what are the downsides for ammonia? Well, there are a few. First off, like I just hinted at, ammonia is liquid between negative 108 degrees Fahrenheit and negative 28 degrees Fahrenheit. If you wanted to shake hands with an ammonia alien, you'd need to do it in Antarctica in the middle of the winter. But that's not good for life, since there would be much less energy available for biochemistry to happen. You could argue solvated electrons might solve that, though. Another issue is that unlike oxygen, nitrogen bonds are extremely hard to break, because fixing free nitrogen gas in the atmosphere, which Earth life needs to do to make nitrogen-based compounds like ammonia, costs a lot of energy. Very few organisms do it because it's so costly. That would be exacerbated by the lower temperatures. Fixing nitrogen on Ammonia World may not be needed, but an organism's biochemistry would somehow have to avoid turning nitrogen compounds back into nitrogen gas. Something that would be a very, very tempting shortcut for chemical reactions. Finally, one of the other problems is that if anywhere on an ammonia world got below the freezing point of ammonia, it would spell the doom for the life on that world. Since, unlike water, ammonia ice sinks to the bottom instead of floating. Earth has frozen up several times in the past, but life survived because ice floats, creating an insulation layer at the top of the water that prevents the rest from freezing. On an ammonia world, it'd just freeze. So, the Thargoids and an ammonia world like the one I have depicted here wouldn't exist. If this is the case, how is an ammonia world better than water if ammonia planets just freeze up before life can really take off? Well, one thing I didn't mention is that ammonia can be liquid at high temperatures if you increase the pressure. Between 10 and 100 times Earth's atmospheric pressure, ammonia can be liquid at room temperature. However, its freezing point is still negative 108 degrees Fahrenheit, getting it far away from the freezing point, especially in a world with such a high surface pressure. If it did freeze, it wouldn't be for long. High-pressure ammonia worlds would probably be more likely than cold, low-pressure worlds, since, like I mentioned, nitrogen gas is a pretty stable compound. So there would probably be a lot of it in the atmosphere of an ammonia world, much more than we even have on Earth, which makes up something like 4/5 of our air. This fixes pretty much all the major issues. It prevents the ammonia from freezing out, and it brings the temperature up, so biochemistry has an easier time fixing nitrogen. So, a world with ammonia life would look something like this. The oceans would be a metallic red color due to all the dissolved metals. Any plant-like organisms would most likely be black, since there is no need to limit themselves to just a couple of bands of the light spectrum because of the solvated electrons. There obviously wouldn't be any ammonia snow, but ammonia makes white clouds like water does. Any aliens from such a world would need pressure suits to stay alive on Earth, like we need on Mars. Besides the fact that oxygen would probably be a poison gas to them. Also, they probably wouldn't need to breathe, because their biochemistry most likely wouldn't require a gaseous oxidizer like oxygen. If they did, it would most likely be something like nitrous oxide rather than nitrogen gas, since nitrogen is pretty inert and doesn't like to oxidize things. Weird indeed. On a final note, most of you are probably not aware I do planet art as a hobby, and I created these detailed Ammonia World images myself. I hope you liked them, and this video. If you did, please press the like button and subscribe to my channel and ding the bell to get notified when I post new videos. Also, please support me on Patreon, link in the description. The more people support me, the more time I can dedicate to making videos like this one. So, until next time, have a great week.